sometimes it freezes. You know?
Oh,
I don't know what is the problem, but it freezes and everything freezes up. And I wanted to close it, but I can't. So I open another one, and it freezes again. And
oh,
I still do the same.
okay. I think one of my colleague will be online. He is actually the creator of that characterization.
Mm-hmm.
So he'll be able to answer and help.
Yeah, we hope so.
Good evening, good morning.
Good,
Good
uh,
evening, good
good
morning.
evening. We're just getting ready for the webinar. So I guess we can get started. Hello, everyone. Good morning, good evening. Welcome to the eFabulous webinar. My name is Rajiv Shrivastava. I'm responsible for online design platform. Thank you very much for participating in the challenge and joining us for the webinar today. This is the second webinar in the series, and today we will cover the topics of circuit simulations. I'm joined by my colleagues Jay Shah and Tim Edwards, who will take us through the presentations today and help us answer any questions. The recording of this webinar will be available on our website shortly after the webinar is over. Over the last 1 week, we received some questions related to platforms. Some of them were related to schematic and some simulations. So and parameter sweeps. So we plan to cover all of them today in our presentation. At any time during the webinar, please feel free to ask questions. You can, of course, ask the questions, or you can type your questions in the chat window to either me, Jay, or Tim, and we will incorporate it in our presentation. We have approximately 1 hour for the webinar. We plan to allow sufficient time for questions. So again, feel free to ask them. If there are more questions and we are not able to answer all of them today, we will put them as part of our email update and we'll send it to all of you. So with that, I will hand it over to Jay for the presentation. Jay, you can, I'll stop sharing the screen and you can take over. Okay.
Thank you, Rajiv. So it's pretty exciting. I hope everyone can see my screen all right. So today we'll be overviewing some of the simulation procedures by using the electric schematic tool. And the intent of this webinar today is to first cover the basic fundamental analysis, which is .dc, that is the DC analysis, AC.AC, which is the AC analysis, and .tran, which is the transient analysis. And I'm pretty sure in any reference-based circuits or even in any reference-based design, DC analysis is the most crucial element that decides how the design is going to flow for the latter half of the schematic design. And we have a library called EF_examples, which I'll show you shortly how to access the library. And we've got certain sample schematics which cover the basics of these analysis. So for .dc, we've got test_differential pair. It's a differential pair circuit. For .ac, we'll be evaluating the AC analysis of a model op-amp. And for transient, we'll be looking at the transient output of an inverter to look at the settling time and see how the inverter performs. And for the sake of design process, especially if someone wants to design their circuits from scratch, we've got advanced setup analysis, which is .opd, that is advanced operating point analysis. And it's by the name of test_.opd schematic in the same EF_examples library. And finally, today we'll be showing you a glimpse of the 2D sweeps that some of the users, asked for, like especially when the challenge kickstarted. They said that we would like to know how the 2D sweep process works and if you have any integrated solution to the schematic design. So we'll be demoing it to you, and that's about it. So let's first start with .dc analysis. So this is test _diff pair. So some of the users might think, where exactly is this ef_examples library? Well, for that, you'll have to go to File, Open Library, and not everyone would be greeted with the same folder view in their Open Library window. So for that, you need to go to Home, Design. Now, Design is the folder where you have all your project files. So for example, when we covered in the earlier webinar, like the project that we'll be working on this challenge is xbg_1v23lc. So this is my project directory. And within this project directory, throughout my project lifecycle, I'll be having all my schematic files in the electric folder, which is ELEC, all my simulation runs and all the simulation raw files in my ngSpice directory. And these are the only two important things during schematic design that a designer needs to be aware of. And when I click on electric, let's say the electric directory, I've got .dlib files. Now these dlib files are nothing but your libraries. So for example, if I want to open ef_examples library, all I have to do is click on ef_examples, hit open, and that's how it opens up the ef_examples library in your sidebar. Now within this ef_examples, we've got test_diff_var, but for brevity of this discussion, we'll just quickly create a new schematic. So I'll say new library, my working library. And the reason we want to do is we don't want to mix our schematic in the same library as the challenge library, so that we can organize our designs and the library, the working schematic library, different from the challenge library, which is xbg_1v. So I'll create a new library called my working library, and then I'll right click here and say create a new cell to create my working.dc cell. And because the first sweep that we are going to do is DC analysis, so the first thing I want to do is add NMOS. I'll drag NMOS from my PDK. Then I'll use tech_ngSpice. Oops. So I can zoom out by hitting the control key and using my middle mouse rounder button to scroll up and down. Yeah, these tips are kind of handy when you are designing bigger circuits and you don't want to use the bind keys quite often. Quick hacks. Now, as I discussed in the earlier webinar, to create arcs or wires, I'll right click on the source node. I'm sorry, left click on the source node, right click on the destination node. And for ground, I'll go to components, add ground. And I'll make sure that there's no body effect, so bulk and source are connected. Now then I'll be naming this guy as VGS, VDS, that's about it. I can even name these nets, which is crucial for some designers who want to like make their designs organized right from stage one of this band gap reference. So I'll name this net as drain, this as gate. Oops. So I can undo and redo if something goes wrong. So gate. That's it. I'll hit save. Now at this stage, when you hit the save to disk button, okay, you'll notice that you already see .delibs already. These are the pre-existing delibs files in your design directory. And if you want to like save this cell the very first time, it will ask you to save this entire library. So I'll say like save my working library.delib, hit the save button. And now I'm ready for my simulation. So I'll go to Explorer. The first thing that some of the users wondered, like, where is the process corners? So for that, I'll have to add analysis process corners from my PDK library tech_EFX@035A, which is XFAB's 0.35 micron technology, specific for this challenge. And the next thing that I want to do is add .dc cell, as we said that we are going to do. So .dc_1d right here. And now I'm going to change. I'll double click on the .dc_1d cell, say what independent source needs to be swept. So in this case, it's going to be VGS. But now here's a thing about ngSpice and electric as a whole. If you want to sweep VGS, the voltage instance of the voltage parameter of the instance VGS, you say VGS. The extra V ensures that you are varying the voltage of the cell VGS. Then I'm going to sweep from 0. I'm going to sweep from 0 to 3.3 volts and step for 0.1 or 100 millivolts increments. I'll hit apply, say OK, and I'll make sure that VDS is at 3.3 volts, 3.3, apply, OK. Before running the simulations, I'll save to library. Then I'll run the simulation button. Yep, no errors. So doing analysis at temperature 27 degrees centigrade. Okay. And it says it's generated number of data columns as 5. This is trivial, but what a designer needs to know is the temperature, which is quite critical in bandgap based circuits. I'll hit enter. And next to simulation, you've got plot simulation output simpro. So this is the waveform viewer, which is integrated with the schematic tool. And once you open this, you can either hit the insert button, hit the insert key on your keyboard, but a lot of mobile users want to go to trace and they will say add, which will show up all the traces that have been saved after .dc simulation. In this case, I want to plot the voltage at the drain node. So I'll hit V of drain and click OK. So V of drain is going to be 3.3 volts because we are not sweeping the drain. We are not sweeping the drain to source voltage. We have kept it as static. So what I can do is, since I don't need this, I can say delete, because a lot of users, have this tendency to add a trace and then, they have a hard time to delete the trace. So you can use the trace menu to delete or add traces, or probably even like add another trace if you need. Now, next I'll do is, now I'll add I of VVDS, which is nothing but current at the drain node, and I'll hit OK. And some of you might think that if this is an NMOS device, why is it that my current is negative? Well, the way ngSpice looks at the drain node is the current which is leaving the drain node is measured by ngSpice. So if you want to look at the current that is entering the drain node, you might want to go to trace, say delete all, hit OK. Now you'll go to trace back, go to evaluate goal function. Now this is a simple calculator that is shipped with SimProbe waveform viewer, wherein you can perform basic arithmetic operations. You can go with special operations like derivative. So in some cases, if a user wants to plot d by dv of the drain current to plot GM, you can like use the derivative function and special operations. And then you can also add constants if you want to like add an expression to your current trace. But at this stage, what we'll do is we'll say negative of I of VVDS, and we can hit OK. And that's how we can plot the drain current versus the change in the gate voltage. Now, if you want to plot GM, which some of the users might want to like characterize their devices before going with the advanced stage of this design, you can go to evaluate goal function, hit minus I of VVDS. I'm sorry. We first need to say special operations, derivative, then I'll go to arithmetic, negative I of VVDS. And this is a good thing. I can even mention the alias as GM and say hit OK. So as you can see here, this is GM and it's plotted on the same plot. If I want, I can split this into a new plot window by saying plot, add plot. So by this way, I've got like two plot windows. It splits this current window into two subplots. And all I can do is just click on this guy, or probably rather click on this guy and drag it and drop it back here. I'm sorry. Probably my mouse pad is sticky. Oops. Let's do it the manual way. I can say move up. I can click on this guy and say plot, scatter traces. Yep, that's it. So this is my ID versus VGS, GM versus VGS. And this covers .dc. I can say save changes now. And that's pretty much it about .dc. Now the next thing that we'll be moving to is .ac. Like once you have .dc analysis, you want to see what does the AC response of your design look like. So for this demo, I'll be using an existing schematic that we have in our EF_examples library, namely test_opamp. And in test_opamp1, you've got a model of opamp and you already have this setup which is ready. You have .ac from tech_ngSpice library. And back here, we can see that the scale is set to decay. So once you run .ac analysis, it will make a logarithmic sweep from 0.1, or I would say 1 hertz, all the way up to 100 megahertz with 100 points per decade. And we have the process corners back here. So at this stage, we are running a typical case of process corners. And I'll just quickly say save, hit the simulation button. That's it. Make sure that temperature is at 27, which is my default room temperature. Now, at this stage, I'm going to do something of a trick situation. I'll say plot simulation. Okay. The first thing a user might want to do is, like some of the other tools say, that if you want to plot AC response, you can either hit DB20, you have to go to your schematic, click on a given node, and then say that at this node, plot me the magnitude and the phase response. Some of you might have to like say that, okay, just give me magnitude or just the phase response. The beauty of SimProbe is it has got AC analysis function built in. So all you have to do is say AC analysis. And if you look back here, you've got V of output op-amp. So if we click back on the schematic, this net is named as out op-amp, and this is where organization is a key thing. If you have your nets and some of the pins which are organized, it is really helpful during simulations. You just have to do V of out op-amp. Now you can either plot magnitude, you can plot the power, which is dB20, or you can plot the phase response of your V output node. So I'll just go ahead and click on dB20. Now at this stage, when you look at the y-axis, it's in linear mode, and you want to make sure that this is in logarithmic mode. So when you double click on either of these axes, let's say I double click on the x-axis, that's when I get axis properties, and I can say from minimum of 1 hertz to 100 megahertz. And I can say, instead of linear, plot me logarithmic. I'm happy with my y-axis values because SimProbe automatically reads the raw file and automatically defines the y-axis range. So I'll just say apply and hit OK. So this is what the booty plot without the phase response looks like for the model op-amp that we simulated. And at this stage, we encourage users to use evaluate goal function to do something like what is the 3 dB point of the magnitude response, and if you want to do crossover, at 2 megahertz, what is my magnitude of my model op-amp? So at this stage, we encourage users to again use trace and evaluate goal functions to perform calculated functions on your AC analysis trace. I'll say no. Or if I want to save this plot, let's say for my future runs, if I want to save this plot, what I can do is I'll go to File, okay, and then I'll say Save As. Okay, now this is where you can save your window. Okay, at this stage, I just want to save this current trace. So I can hit traces and I can save whatever trace that is visible, just save this trace. Okay, and storage is the place where you will save your current trace. Now some of the designers might have the habit of performing multiple runs on their designs, like probably 30-40 runs. Like I knew back from my grad school, one of these guys from Qualcomm used to have 60 to 80 runs on the same design, even when used to make smaller changes, like just changing the value of a resistor by probably like 1.3 kilo ohms. So they have the habit of creating a separate directory and tracking those changes over time. So at this stage, if you are one of these designers who wants to incrementally design their circuits, so in that case, you can say storage. I'll go to my home directory, which is why I'll go to either my home, design, and back here I can create a new directory called my tracked design changes. Okay, I'll create this directory. I'll click here and I'll create like AC underscore analysis underscore run. So bear in mind, I mean, this is just one first time way. I mean, once you set up these directories, like, it's just a piece of cakewalk to save these simulation results. And now I'll say, so if you want to save the set of sweeps, you have to create a new directory saying run underscore one underscore. After run underscore one, I'll add it as initial work. That's it. And I'll say choose. That's it. And I'll ensure that I hit click on traces and make sure it's visible. And I'll hit save. And it will ask me, do you want to save this thing? I will say yes. Okay. And once I exit out of SimPro, okay, next time when I'm using SimPro, and let's say if I open SimPro, if I want to access my previous results, I can go to File, Open. Okay, I'll go to my home directory, Design. I'll say my track design changes, AC analysis run. This is my first run, initial work. And all I have to do is click on data.epp. This is where SimPro will understand what is it that you have saved and what is it that you have to plot. So in piece, in bit of a moment, you can just plot your previous runs. And the beauty of this is, even when your ngSpice directory is cleared out of your previous runs, at least your result is saved as a static waveform or a static trace. Unlike in some other tools wherein you need your raw files and your trace runs, you don't have to worry about that. SimPro ensures that everything is saved within the same run directory. So that's pretty much about EC analysis and how to save your results using the SimPro waveform viewer. The next thing that we are going to cover is the transient analysis, which for some designers would come at the later stage, but it's better to cover the basic analysis today so that you have a head start to just crazy out on your crazy ideas on bandgap references. And now at this stage, I'll go to test underscore inverter. So as we can see here, this is a two-stage inverter. Okay. So a couple of this thing, when you look at test underscore inverter, okay, you've got two-stage inverter, and then you've got your transient analysis. I think my screen resolution might have messed. Anyways, since this looks a bit garbled up because of my screen resolution, I'll just quickly overview .tran, which is right here. Now .tran consists of a straightforward approach, which is T-start, the starting time, T-stop. So if I want to, let's say, run my transient simulation for 20 microseconds, I'll say start at 0, stop at 20 microseconds, and t-step is 1 nanosecond. So this is nothing but the strobe rate, which some of the users from other design tools are aware of, or probably the sample rate at which the transient simulations will like fetch the data points. And at this stage, we just need t-start, t-stop, and t-step, which is nothing but the sample rate of your transient simulations. And I'll go back to test underscore inverter. So any analysis, time and again, I would like to remind designers to add process corners, because this is how the schematic editor tool will understand like what PDK it is talking to. In future releases, if we have more PDKs on board on our platform, we have to ensure that process corners is added so that the schematic design tool understands what particular PDK is in use and what are the process corner definitions for your simulations. So at this stage, I'll just say save, hit simulation. That's it. Now, this is something which is unique about transient simulations. When you run transient simulations, you can even look at the initial set of transient solutions or the initial conditions when your transient simulations has just begun. This is really critical when you have capacitors in your circuit, especially if you look at the bandgap references. A lot of designers might have strict conditions at the startup circuit of your bandgap reference design. So if you have startup problems, you can actually analyze your initial conditions using this initial transient solution setup in your log directory. And let's say if you accidentally say like I hit enter and I exit out of it, you can always go to the log window, which is the tiny little guy right here. And if you want to say that I want to also track my changes, what were the initial conditions when I changed certain aspect of my design, I can always go to file, I can say save as, and then I can go to my design directory. I'll go to my track design changes, EC analysis runs, run underscore design one. And back here, I can say that test underscore VP, or I can say run underscore one log. I'm sorry, I'll say create no folder for run underscore analysis underscore run, because we don't want to mix up our transient log with AC analysis log. So at this stage, I've created a directory called trans underscore analysis underscore run. And then I'll say, just save this log file. So that in my future run, like if I want to access what my initial conditions were for when my design started initially, I can just go back and look at the initial conditions. I don't have to like make changes on my schematic, run the simulation again. I mean, that's too cumbersome. We don't want designers to waste time into like, rechanging their test bench and simulating it again just to see what was that initial condition that might have given me a better result. So that's one of the key aspects we encourage designers to have an organized way of structure while creating the design, so that if you are collaborating with other designers during the project life cycle, at least you don't spend time in going back to your test benches, making those changes and coming into a collaboration meeting saying that, oh, okay, let me just go back and see what happened. So that's what we want our community. That's the whole intent of eFabless, a community-driven, a community-based design approach, as opposed to that engineer in isolation, which existed back in 80s and 90s. But today we want a community to come up with a unique design and show it to the world that we've got something in our under the hood. Anyways, back to the discussion of using electric. I'll say save library because I made a minor change back here. And that pretty much covers our basic set of analysis. And now advanced set of analysis, which is .opd. This is nothing but the operating point analysis.
Jay, can I interrupt you for 1 second?
Yeah.
Sure. Shall we take some questions if there are?
If we have any questions, we can just go ahead with the basic analysis.
Yes.
Let me just briefly cover the operating point analysis because that would complete our discussion needed for challenge.
Jay, excuse me, Jay. There is one question, so let's take it.
Oh, yeah, sure. I wasn't aware of it. I'm really sorry about that.
Yes, I have a question here. Can I ask it?
Yeah, go ahead.
Go ahead, please.
Okay, the question is about, it's good to save some voltage waves like you have shown already. And if I want just to update this figure or this drawing according to some adjustments I've done to the schematic, I want to see this same waveform according to a change I've done in the schematic. I don't like to reopen the same wave again and again after some adjustments.
Okay.
How can I do that?
Okay, so you mean you have multiple versions of your same design, right?
I mean, I adjust my design for some W for the transistor or some resistor, and then I re-simulate the same circuit, and I want just the figure to update itself to show me what is the result. I don't want to reopen the waveform every time I re-simulate.
So so yes, let's say once I run this simulation, okay, and now I open SimPro, okay.
Yes.
I'll say go to trace, evaluate, and I'll say I of for example, I've done this. Now I'm going back to my schematic. I say that instead of 3.3, or rather I say instead of 3.3 volts, I'll make it as 2.7 volts. Okay. I'll hit simulation. Okay.
Yes.
But then I'll go to my SimPro. Okay. And I'll say, go to plot and say reload. So this will ensure that whatever is my current run, okay, my simulation will adjust to the current run's output.
Yes, another question: how can I change multiple devices or multiple instances at the same time? If I have more than one transistor in the schematic, and I want to change the length of all of the transistors to just one length, or the width to be one width, how could I do that? Because I couldn't do that when I tried to do.
So for global conditions, okay, I mean, we are working on a robust way to. I've already taken a note of that because that's something that even I experienced. And for global conditions, like initially, I mean, one of the methods that I tested, which is not foolproof, is you can mention this guy as X, okay? And then you'll need a spice wrapper around it to say that, access this global parameter called X from the net list, and then change all the X's. So let's say if I've got 3 NMOS devices, which is what we used to do in some other tools, that we've got global variable like X for NMOS 1, X for NMOS 2, X for NMOS 3 length. And then the way we are working around it, and I've made a note again of it, is you can just add a small this thing that vary x back here. If you want, I can just show you up in one of the other instances, okay, how we are working, how we are developing this. Like if you want, like either the width, length, or the number of fingers of multiple transistors to be varied in the same length. Or
Yes, so, Jay, there is a question on the chat. One question is how to create parameter, for example, W, L, etc., and sweep internal parameters.
So for sweeping internal parameters, okay.
Actually, first create and then sweep.
I mean, this is again what I was going to demo to the users today.
Okay.
And this is something that we are just fine tuning it to ensure that it works for broad range of devices. So back here, we've got something called as 2D sweeps, like parametric sweeps, as a lot of users might be aware of. Okay. So back here, you have this basic setup, but your first sweep is nothing but you are sweeping VGS. And then your parametric sweep is like you've got this device called M1 and you are sweeping the width of this device from 1 to 10 microns. Obviously, if you have more devices, you can just make this as a global parameter called width width, okay, and you can say that vary the second sweep parameter as width. But for sake of now, I'll just show you how this demos out or looks out once you simulate. So when you say simulate, right, when you save it and say simulate, hit OK. Oops, sorry. So since it's in development, I mean, this is not going to be the same way that once we release out, it's going to be pretty straightforward. But since it's in development, I'll just show you up how it works, the multi-parameter, especially like when you have to access parameters of the device, that's when it's critical. So AIC_test schematic. So this is something you can just ignore. I'll just run something real quick. So what I did back here is that I'm plotting the ID of device M1, a transistor called M1. I'm plotting the drain current of device called M1. And then I'm changing the width of M1 from 1 microns to 10 microns, okay? So I'll just say Control A and hit OK. So if I say that for 4 microns, this is my plot, okay? For 2 microns, this is going to be my plot. And obviously, once it is released, a user, and thank you for bringing this up. We also have one of these analysis test benches wherein a user can create a global variable, like either the width, length of active devices like MOSFETs, or the width and length of passives like resistors and capacitors in case of poly devices or in case of diffusion resistors. Or users can also go ahead and change some of those device parameters of BJT, especially like parallel, when you have like multiple BJTs in parallel, something similar to that. So yeah, that would be like, due in a while so that, you can perform multi-parameter sweeps and access device parameters, small signal parameters from MOSFETs, or probably range of other device things like net voltages. And then you can combine all of them, use a calculator function to like perform goal-based analysis, that saying that if I'm looking for ID, let's say for example, if I'm looking for ID at 1.2 volts, So, and I can perform a cross function like what width will give me the so-called current, branch current. So I can even perform that goal function using trace evaluate goal function. I hope that answers your question.
Another question, if I can ask, or you will give us some time at the end to ask more questions. You want to proceed with the presentation or take more questions?
No, if you think it's critical, sure, we can go ahead. But I just wanted to like cover up something, the dot operating point analysis, because I think that is something, we have it ready so that if you have to do these operating point analysis for quick simulations,
Okay.
that would answer your basic. But if you still feel worthy, like it's a continuation to our current discussion, why don't you go ahead and just ask us a question so that everyone will be like fruitful with that discussion.
Okay, I think we can have the questions at the end to let you proceed with the presentation, and I have some questions at the end.
Sure, sure.
Okay.
Thank you.
Thank you.
Now the last thing that I wanted to show is, and then come back to questions since it's question time. Lots of questions than we anticipated. So I'll go to test_.opd. Now this is, as some of you might have just guessed, it's that Weidler current source from the famous Bob Weidler. And a lot of times before even doing DC analysis, you want to do like quick operating point analysis. You just have your sources laying around. You just want to do quick sweep in sources to see if your devices are operating in saturation, or if the drain current is what you needed for your basic hand calculations. So we've got something called as .opd, which is again found in the test bench right here. .opd test_ngspice library, and it's got 4 sections, namely the MOS devices. So in MOS devices, okay, you can say what is the name of my MOS device. So in this case, for example, I've named my MOS device as M1. Okay. So in this case, you'll say, if you want small signal parameters of your MOSFETs, you can say that give me the drain current passing through M1. If you want the small signal transconductance, you say give me the transconductance of M2. Give me the width of M3, just in case if you have forgot that what is the width that you've assigned. And give me the drain saturation current of M4. So you've got our devices M1, M2, M3, M4. Then you've got M source and M sink, and you've got something called as, I can use hand tool to like quickly drag and this thing. You've got what you call a BJT, wherein the collector and base are connected to make it work as a diode. So you can also access the BJT. So in this case, I have to say the name of the BJT, the name of the BJT device, and what kind of BJT I'm using. If I'm using QP1, QP2, QP3, QP4, which is NPN device. And then I can say that what is the voltage difference between 2 nets. So in this case, I've named this guy as X, this network as X. I've named this guy as Y. So I can say find me the voltage difference between nets X and Y. Okay. So at this stage, if I've zoomed in completely, I can use the bind key F to fit all my stuff back into best fit view. So, and the final thing that we have back here is branch currents. Okay. So I can use something called as iProbe, which is again a cell in tech_ngspice library. And so let's say if I've got multiple resistors here, and if I want to see what's the current flowing through one of the branches. So this is very fruitful when you have multiple branches, devices spread across multiple branches. I can add this iProbe within that branch, name it as, for example, I've named this thing as knee resistor. And I can say like, what is the current passing through this knee resistor? So I can ask this analysis to say, get me current for this knee resistor. And finally, I can track the region in which my active MOSFET devices are operating in. So in this case, what I've done is I've said like, just track me the regions in which all my devices are operating. So M1, M2, M3, M4, M source, and M sync. And now when I run simulation, okay, within this simulation log window, I've got all my small signal parameters. So the ID of device M1 is what do you call 250 nanoamperes, I believe. GMS is the width of M3 device. This helps me like, okay, I set the width of this guy as 1 micron. VD-SAT of M4 is 100 millivolts, close to 100 millivolts. It also tells me what's the instance parameters, the basic SPICE-based instance parameters of active devices like MOSFETs and BJTs. It will tell me what's the net voltage between X and Y, which is 3.43 volts back here. The probe current, so the current that is going through the branch connecting the knee resistor, as we have seen in Weidler current mirrors, is 200 nanoamperes. And finally, this is what designers need, and this is what I always used to need. I want to ensure that all my devices are in saturation. So it will tell if, so back here only M3 and M4 is in saturation. M1 is in cutoff, but it also tells you if it is in cutoff, whether is it in weak inversion, strong inversion, and what is that factor. So back here it will tell you device M1 is technically operating in cutoff with VGS being 0.07, which is nothing but 70 millivolts less than the VTH of that device. So based on the small signal VTH calculator, based on the width of the current device, it will tell you by how much is VGS less than the VTH of the device. So that designers can know if it is in weak inversion, if it is on the onset of inversion, or if it is in strong inversion. So yeah, that's pretty much .op analysis. And again, you can save the track of your operating point by creating OP runs and saying that run 1 when width was so and so, run 2 when I changed the voltage of this thing from 3.3 to 2.8, something similar to that. I mean, obviously you can explore around, you can add more devices and see how it works for you. And we would love to hear feedback on advanced analysis, because that's something we are trying to tune so that you as designers can worry less about the tool and more about creating great designs for this challenge. That's pretty much it, and we'll open up for questions. Questions?
Yes. Can you hear me well?
Yeah.
Yeah, please go ahead.
Okay, how could I make an array of an element? I mean, if I have a MOSFET and I want to make 3 MOSFETs in parallel or 3 resistors in parallel, how to make an array of an element?
Okay. So at this stage, if you want to make array like in parallel, we encourage users to go with the old way of, manually adding these devices. So in this case, let's say if I want to create array of this guy, the resistor. Okay, although we ask users to do it manually, I can simply hit Control C, Control V, Control C, Control V.
Jay, I think there is another way of doing it. Let me see if Tim can answer that question. Because
Yeah.
I saw one email that he had sent about array devices. So I'll try to get that answer from Tim.
Sure. Yeah, I mean, so far I prefer manually. Okay, and in case of BJTs, okay, you can use, I believe, the mult parameter. So it will like multiply, it will create parallel structures for the same BJT cell. But yeah, that's what it is. And
Okay. Mhm.
yeah.
Another question. When I opened the project manager to import the project, like you have explained in the first webinar, I found in the pending imports 2 projects. I found 2, not just one. In the pending imports.
Okay.
Yes, I found 2 versions. It wasn't just one.
Yeah, actually there was an issue on our, not an issue, but a design issue, I'll say, where if you accepted the challenge twice, we were importing it twice. I believe we have fixed that problem, and I can reconfirm. But yes, there was an issue that if you accepted challenge twice from the main web page, it would import it twice. So you can ignore one of it and work with one.
Yes, another question. When I click on simulate in the characterization box, sometimes it freezes, and I can't close it. How can I force close something?
Rajiv, you have a better listing on Open Galaxy, so.
I will have to find an answer. I believe we can open the terminal. So you can right click on the main screen and bring a Unix terminal and find the process that is running and kill it. But I'll surely find a better answer for that. I thought Tim was joining us because he is one of the developers of the characterization tool. I thought he might be able to help. I'm just trying to contact him on phone, see if he can join.
Okay, another question. The characterization tool, we don't have access actually to the test benches, right? We just click on simulate to simulate some specification, but we don't have access to test benches or how this test bench is done, right?
Yes, and although when you run simulation, so if you go to run design, okay, and I would like to add this, that this is only when you have your local library called my working library, and you have your schematic inside my working library. Okay, we encourage users not to create schematics in the same library as the challenge. Okay, but once you have that schematic, okay, when you go to the design directory, you go to your home directory, you go to design, then you go to the challenge directory, okay?
Yes.
The XBG, and now you've got something called as SPI. So SPI, okay, contains, I'm sorry, not the SPI, my bad, but you go to test bench, Okay, so test bench contains all the spice, this thing. So you can actually use this test bench to probably pin out into your local. So let's say if you don't have your entire bandgap reference ready, maybe with your spice expertise or basic understanding of spice, you can change the netlist to map it to your current design. Let's say you just have your op-amp and you want to run what do you call, sorry, let's say you just have a basic reference circuit and you want to run temperature coefficient, TEMCO simulations. Use one of these test benches, remap your pins with little spice modification to your current circuit. And then you can run this netlist with what you call the current simulation. But thank you for your input. At least now I know that some of you are interested into looking at test benches and integrating it with your current working design. Even if it is not complete, you want to like reuse some of these test benches and simulate it so that you can save time. Yeah, we'll make sure that in our next webinar we come up with a solution to reuse these simulations. But if you want to explore the test benches, just to make a note, design XBG test bench, and this is where you have your test benches.
Yeah, that's pretty nice. You mentioned in the previous webinar, because I haven't attended that webinar, so I have a question related to the material said at that webinar, which is when I click on submit, the circuit, it just uploaded to somewhere, and you have a version under, and when you click another submit, you have another version. So you can delete those versions from the ACE. I think it's called ACE. That's where
is automatic characterization engine.
Yeah. Is it available to delete these versions, or you don't have access to these versions again once you submit it?
So once you submit it, right? So I'll just take a small quick detour, because let's say you go to the website, okay? So at this stage, I'm just going to show you one of my previous runs. I'll go to Open Challenge. I'm sorry, I'll go to Toolbox.
You'll go to Challenge Management, right?
Oh, sorry. I'll go to Challenge Management. Yeah. And I'll go to Simulation Results. Okay. So this is my previous run. Okay. So it gets stored here. You don't have to worry from your Open Galaxy that if I resubmit it again, do I have to delete my previous runs? No, you don't have to worry about it. But whatever that you submitted previously gets uploaded here, so that you can keep a track of your previous runs, what all changes you have made, but you don't have to worry about it in your Open Galaxy environment. Existing run files and then submit it again. No. I hope that answers your question.
Yeah, go ahead.
Is it available to have something like an all MOSFET voltage reference? I mean, do we have to use BJTs in the design, or it is allowable to use all MOSFET voltage reference?
Yeah, I mean, it is up to you as a designer. Like, I've seen a lot of people going with MOSFET only solution. Some users use BJTs for the great, to get that PTAT circuit live in action because of the TEMCO performance of BJTs. But if you are comfortable with MOSFETs, yeah. And I might want to like confirm it back with Rajiv and some of the advanced analog designers back at eFabless.
I think both are allowed. You can use BJT, you can use MOS. Your question on the design data that you have submitted, did you mean you wanted that data back, or Did
No.
you? Okay.
No. I wanted to delete it. I
Oh,
mean,
you wanted
if
to.
I want to delete it, can I do it or not?
At this point, we have not added a delete button. I guess we could. Right now, we are saying the last submitted design will be considered as your entry.
I think you mentioned in the previous webinar that when you click on submit, more simulations are done on your circuit more than the ones you have in the characterization box.
I believe it's the same. Tim,
Yes,
Tim
it's
has
the
also
same.
joined the call.
It's the same.
It's the same.
So once you finish the design and you pass all the simulations and the specs, you can just click on submit, and the same results are getting, and you pass also the specs on the site, right?
Right. Actually, so you're absolutely right. We do the exact same runs on both. So whether you run ACE locally or you submit and we run the ACE.
So no difference.
No difference.
The only thing
The only reason why we are redoing it is just to guard against any local changes to the that may have happened.
So as we saw here, right, that I'm sorry. Remember the local set of test benches that we have? Sometimes you might want to just, we encourage users again to like do those changes on those test benches on the local library. Okay, but sometimes what might happen is that when you look at those individual test benches, you might just want to change your temperature range by a certain factor in your working library. So in order to guard the official submission from these local changes, we make sure that we upload your schematic into our server and run the same set of tests,
Yes, I got it. So if I did some changes to the test benches, we want to make sure that everything gets back again, and you simulate against the required for the challenge, right?
Yeah. Tim, before you joined, there was a question on characterization tool hanging up. So Ibrahim, if you want to ask again.
Yes. Yeah, the question is, when I click on simulate, sometimes I find everything freezes, and I open another characterization box to resimulate to see what is the problem, and it freezes again. So I have about multiple characterization boxes opened, and I can't do force closed for them. So I was asking how to force close any of them or all of them.
Oh well. First, if you get it to hang up like that, make a help ticket, because we want to work through and figure out why it's doing that. Because I put in some hooks into the code that can let us see what it was doing at the last time that, or while it was hung up. As far as killing the process, though, you can do that through Unix commands. Again, if you're not that familiar with finding processes in Unix and killing them, I can just, again, send me a help ticket and I can work that through with you.
Yeah, maybe we can post it somewhere that if we want to cancel ACE, then here it is how we do it in the Unix method.
Well, for ACE, for the remote ACE, there is a cancel button. For the local ACE, there is not, because it was not expected that it just hangs up in the middle.
Right.
For that, though, you can do a Unix kill command.
Yeah, we can just share the process name or something. Great. So, Ibrahim, we'll follow up with you on that.
Yes, you mean I have to know what is the process PID number, and then I kill that process, right?
Yes.
Right.
Yeah, okay. Thank you.
Or if Tim can come up with a better way, maybe.
Yeah, there was a switch actually in the Linux I used to use when something hangs, what was called force quit. When I click on it, it says to me, hey, press on the window that you want to force close. And I just click on it and it closes. So I was searching for that button, but I can't find it, or I don't know how to show up to make it available.
Yeah, you need to do the PS command, which gives you the process. So you say PS and then find the process that's running the simulation, which I think if you find the ngSpice process and kill that it will proceed to kill all the tools above it. But then again, if it's hung up, I'm not sure if they'll notice that the process below them is quit. So again, it's something I would like to work with you first before you start killing your processes to see what I can find out about why it hung up.
Yeah, and also something happened weird when I tried to simulate something like the leakage current. It says that it's failed or something like that. I don't know.
Leakage current might generate some fairly strange answers because this is a MOSFET, a 0.35 MOSFET process, and there isn't much leakage at all. So basically, you end up with zeros, and sometimes that causes ngSpice to have troubles. Generally speaking, that shouldn't, unless that happens to be causing the simulation to fail all the time. In that case, I'd like to look at it. At least when I was running it, but then maybe the circuit topology could be different. But when I was running it, it was just giving some messages, but always giving me back an answer that was just zero for the current.
Okay. It might be my fault because I'm using very basic things to try the tool and to go through the whole process to see if I will get troubles in the future. So I wanted to ask you. Okay.
Well, so that's fine. Yeah, no, I'm quite happy to have people stress test the system, and just be aware that the system has not been running very long. So when you stress test it, you are fairly likely to come up with errors, and the more you can get those errors back to us, the faster we can fix them.
Tim,
sorry, I just wanted to make sure that I understand how to change multiple devices parameters at the same time. I couldn't get it actually. I think the person who have been given the presentation explained it, but I couldn't get it. I didn't get it. How to change multiple device parameters at the same time?
Multiple device parameters at the same time. Jay, that is the question.
Yeah. So the thing is that we are like fine-tuning a way to create global variables. So because electric and ngSpice have been integrated, right? So we are trying to work out with electric in such a way that when you create global variables, right? So when you have, let's say, let all the lengths of the schematic be called as length.
And then how to access that parameter? I mean, if I called all the length to be L1, for example, so how to access this L1 and say to Spice that L1 equals, for example, 1.2 microns. Okay. How to do that?
Let me just... So the reason I didn't want to this thing is because it involves telling the model that, hey, I'm asking you to change the length of your device.
Sorry for asking.
No. I mean, it's a great question, and that's something that we were pipelining ourselves.
It's really annoying.
No. I mean, it's actually good to have questions. No questions means something is wrong. Something with the presentation goes wrong. Must have gone wrong if there were no questions. So let's say if I have this guy, okay? I can add a Spice block. And again, this is highly experimental, which we don't encourage users. So this is the reason I'm mentioning this is someone just mentioned in the chat that you want to see how that dot control block works. Okay, so once you have the dot control block, dot control end C, I believe. Correct me if I have not written it correctly. So if I want to say, I believe someone did.
You
There
talking
is a
about using
question.
the dot alter command?
Just a sec.
You can use the dot alter command within
Dot-
the
yeah.
control scheme.
Yeah, thank you. Finally, we've got even NG space experts back here.
Now, the problem is the way the models are defined is as
Yeah.
a circuit. So, you know, the device like M1 would be XM1. And
Yeah, so
the models are hidden. I don't have access to like the actual model name.
and that's why I wanted to, like, bring this thing. Even if it doesn't work, at least you'll know how this PDK is structured so that you can access those parameters. So alter @m, which is the device identifier. Okay, next I'll add X. Now if this device name, okay, is named M1, okay, so I just want to make a quick change because that might lead to confusion. Sorry, M4. So I'll say dot control and end C. Do I need a period before dot end C?
Yeah, you need a dot NC because that's the control
Yes.
block.
Alter
Yes, you do.
M dot X, which is the tells that it's a subcircuit. And if I want M4, I'll say M4 dot M1 width equals 5 microns. Now I'll clarify this a bit, that M4 is the name of your device, okay? And no matter whatever you do, M1 is the way the current challenge owner has designed the PDK. Like, he
Yes,
modeling such that M1 is a subset of device.
So Jay, if I may interrupt, so it is true that all devices are a subcircuit definition, and Jay, we can probably share a list of all these device names.
Yes, I mean, we can definitely come up with a comprehensive list.
Okay. Or at least the list that we think is most used devices, right?
Yeah.
Okay.
But see, this is for someone who is comfortable with Spice, and I know a lot of users might be transitioning from different tools. So we are we can release this, and we are having what you call set of GUI such that you don't have to worry about these, because some of the devices, the way they have been modeled, have a different device identifier, and they've got like two set of hierarchies to the way they have been modeled in the PDK. So in order to ensure that users don't have to worry about it, we are just adding these fields wherein you just name the name of the device and you name what is the parameter that you want to vary or alter.
Yeah.
And the analysis will take care of it.
Sure. So
Yeah.
while we are working through it, I think it is a good idea to share the model names.
Okay, sure.
Hey, could I also just say I want to export the Spice deck and just do simulations on the back end through the terminal with like a text editor? Is that possible? I can just do like any Spice.
Yeah, sure. Yeah, you can do that.
Yeah.
Spice.
Well, you're still going to have only access to ngSpice on our platform.
Yeah, the same basic commands though are about this. Like,
Yeah, you can just run ngSpice from the command line. I do that all the time.
Yeah, because I tried to do this type of parameter sweep where I tried to alter like the W of just a single characterization from like 1 micron to 10 micron using like the control block. And I know in the ngSpice forums you have to do like a while loop or something with the .alter command.
That's right.
The problem was, since I tried to use that vector, the @m.xm whatever, but because the model names were hidden, I didn't know whether it was like .model CMOS N or CMOS P or whatever was, or PMOS or NMOS.
Right. Well, that's what we're saying. Is that the problem here is that XFAB has modeled all of their devices as subcircuits so that they can throw in extra parasitics as some kind of model. And so, yeah, there are devices underneath the subcircuit that is transistor, and they're hidden to you. So that was what Rajiv was suggesting, was that we would just go ahead and write up a list of what you would need to know to alter the basic parameters of the device, because otherwise, if we can't show you all of that detail because that's all proprietary XFAB information. But if we just say, here, this is the model, this is the path to the name that you need if you want to alter a specific device width or length or one of the obvious things that you would be changing, then we can do that.
So I can't do something like .param, WG is equal to whatever, and then just do a step in ngSpice of that. Like, 'cause I know ngSpice doesn't seem to have like a dot step type thing or something.
A dot what?
Like in
parameters.
Spice or T-Spice, I can do a dot step param on a variable within the circuit. Like if I say W is equal to like WX, and then I want to just vary WX from like 1 micron to 10 microns, I can do like an A-Spice, like a dot step or whatever within like the DC sweep.
Yeah, there are ways to do that. Actually, within a DC sweep, I'm not sure. I would have to look at it. I mean, one way to do that is just to do a loop over different operating points instead of a DC sweep. Yeah, I've looked at different ways of doing all these things in ngSpice for the test benches, and whoever is somebody needs to go on mute. Somebody needs to go on mute if you're not part of the conversation right now. There are, ngSpice syntax can be really obnoxious compared to some other forms of Spice. So again, if you want to send a help ticket, we can work with you to do that. If it's something that's really general purpose for everybody, we could potentially do a webinar on it.
Great. I just want to make sure we cover all the questions, but I think they're running a little bit over time. I do not mind, but if you have more questions, we are happy to take them.
Just one final question.
Sure.
Would you have like maybe a repository of Spice decks? Like, let's say like the optimal way to do like a while loop sweep of like the length or the W or a device parameter. And then you can just, like import that as a Spice code into our simulation.
I believe that Jay has few of those.
So we can release it shortly, but let me just show you up real quick so that I can clarify if that's what is needed. If you can just give me a moment. So this is for MOSFETs. You've got these parameters, and we'll be releasing it shortly, like the parameters that you can access for MOSFETs, for BJTs. I hope that answers the question. Is the small signal device parameters?
I think Jay, the question was slightly different. Question was, can we release some of the Spice code that does these parameter sweep, and that user can change? So just like a while loop or for loop.
Yes, and so we don't want, I mean, unless user demands that they want Spice code, writing in for loop based thing, and then again, a question comes to the proprietary of XPAP's PDK. So that's the reason, like, we are creating.
Yeah, let me work with you. I think
Yeah.
I think there is something that we can do, but we will we'll create some and we'll share with the.
Yeah, sure. I think that needs further discussion so that we can come to a common distinction.
Yeah, I think it's fairly easy for us to set up a repository somewhere where the users can take a look at it and get some example bits of code. There's also the test bench itself has a number of different types of loops and ngSpice, so you can look at that. Whenever I want to look at come up with something new in ngSpice, I usually go online and look for some kind of answer, but that can be kind of iffy. There's not a whole lot of information out on the web about how to write interesting and unusual things in ngSpice.
Yeah, but forums is a great starting point. Like, forum members at ngSpice have been really helpful in getting some of those basic analysis get done. But we'll definitely open up for a discussion how to like integrate that Spice coding with the PDK that's being used for challenge.
The ngSpice manual is pretty helpful too.
That's pretty much my go-to source is the ngSpice manual, but it's often difficult to figure out some things, particularly when it gets into the syntax of set and let and what's a vector and what isn't. That it can get really difficult. So yeah, I agree. Code examples are good, and we will consider that as a there that we should make a repository of different Spice scripts.
We can share that repository of just basic codes. All right. If there aren't any more questions, I would like to thank you everyone for joining the webinar and participating into it. It was great. I will post the video of this webinar on our website, so it'll be available for review. And I think we have made notes of some questions. We will try to answer them through email. And again, thank you very much for joining today.
Thank you, guys.
Bye-bye, everyone.
All right, take care.
We'll see you in the next webinar. Thank you.
Have
Bye.
a nice day. Goodbye.